Space, the final frontier. It's vast, it's dark, and it's anything but empty. In the vacuum of space, where there seems to be nothing, there is actually a tremendous amount of energy. This energy, known as vacuum energy, is one of the biggest mysteries in modern physics. It's a concept that challenges our understanding of the universe and its fundamental laws. Think about the air around you. Even though you can't see it, it's made up of tiny molecules constantly moving and colliding. These collisions create a certain amount of energy. Now imagine removing all the air, all the molecules, everything. You're left with a perfect vacuum. But even in this seemingly empty space, there is still energy. This is vacuum energy. The existence of vacuum energy has been confirmed by various experiments, including the famous Casimir effect. This effect demonstrates that two metal plates placed very close together in a vacuum will experience a force pushing them towards each other. This force is attributed to fluctuations in the vacuum energy. It's like the plates are being pushed together by the invisible energy of empty space. The discovery of vacuum energy has profound implications for our understanding of the universe. It suggests that even the emptiest regions of space are teeming with activity and energy. This energy, in turn, affects the expansion of the universe and the behavior of galaxies. It's a force to be reckoned with, a force that we're only beginning to understand. Imagine a vast, dark ocean stretching out in all directions. That's a good way to picture the universe. Now imagine that this ocean is filled with a hidden energy, a force that permeates every corner of space. This force is vacuum energy, and it's one of the most important concepts in modern cosmology. Vacuum energy is a form of energy that exists everywhere in space, even in the absence of matter and radiation. It's like a background hum of energy that's always there, even in the emptiest regions of the universe. This energy has a profound effect on the universe as a whole, influencing its expansion rate and its ultimate fate. The discovery of vacuum energy came as a surprise to physicists. For decades, they had assumed that the energy of the universe was dominated by matter and radiation. But in the late 1990s, astronomers made a startling discovery. The expansion of the universe was accelerating. This was unexpected because the gravitational pull of matter and radiation should have been slowing the expansion down. The accelerating expansion of the universe suggests that there must be some other force at work, some other form of energy that's pushing everything apart. This mysterious energy is what we now call dark energy, and it's thought to be closely related to vacuum energy. In fact, many physicists believe that dark energy is simply a manifestation of vacuum energy on a cosmic scale. The discovery of vacuum energy and its connection to dark energy has revolutionized our understanding of the universe. It tells us that the universe is a much stranger and more complex place than we once thought. It also raises many new questions such as, what is the exact nature of vacuum energy? Where does it come from? And what role does it play in the grand scheme of things? To understand vacuum energy, we need to understand the fundamental forces of nature. These forces govern everything in the universe, from the smallest subatomic particles to the largest galaxies. There are four known fundamental forces: the gravitational force, the electromagnetic force, the weak nuclear force, and the strong nuclear force. The gravitational force is the weakest of the four forces, but it has the longest range. It's responsible for the attraction between objects with mass, such as the Earth and the Sun. The electromagnetic force is responsible for the interactions between electrically charged particles. It's what holds atoms together and gives rise to light and other forms of electromagnetic radiation. The weak nuclear force is responsible for certain types of radioactive decay. It's also involved in the nuclear fusion reactions that power the Sun. The strong nuclear force is the strongest of the four forces, but it has the shortest range. It's responsible for holding atomic nuclei together. These four forces are thought to be mediated by particles. For example, the electromagnetic force is mediated by photons, which are particles of light. The gravitational force is thought to be mediated by gravitons, although these particles have not yet been detected. Vacuum energy is thought to be related to the quantum fluctuations of these fundamental forces. According to quantum mechanics, even in a perfect vacuum, there are always virtual particles popping in and out of existence. These virtual particles can interact with each other and with the fundamental forces, giving rise to a non-zero vacuum energy. Section 4. Fields of mystery, axions, inflation, and quintessence. The universe is a strange and mysterious place. Among these are the exotic fields known as the axion field, the inflaton field, and the quintessence field. These fields could hold the key to understanding dark matter, the origin of the universe, and the accelerating expansion of space-time. The axion field is proposed to explain the lack of CP violation in strong interactions. Axions are potential candidates for dark matter, inferred through their gravitational effects. The inflaton field is thought to have driven early universe inflation. The quintessence field is proposed to explain the accelerating expansion of the universe. These fields represent exciting areas of research in modern physics. Section 5. Quantum fields. A sea of virtual particles. In the strange and counterintuitive world of quantum mechanics, empty space is anything but empty. Even in a perfect vacuum, a sea of virtual particles constantly pops in and out of existence, like fleeting phantoms dancing on the edge of reality. This restless sea of quantum fluctuations is described by quantum field theory, one of the cornerstones of modern physics. Imagine a calm, still ocean. Now imagine that beneath the surface a constant churn of waves and ripples is taking place, even though there's no wind or external force to disturb the water. This is a good analogy for the quantum vacuum. Quantum field theory postulates that every fundamental force in nature is mediated by a corresponding field. These fields permeate all of space and time, even in the absence of any matter or energy. And just like the surface of our imaginary ocean, these fields are never truly still. They are constantly being jostled by quantum fluctuations, tiny ripples of energy that pop in and out of existence. These quantum fluctuations are a direct consequence of Heisenberg's uncertainty principle, which states that certain pairs of physical properties, like position and momentum, cannot both be known with perfect accuracy at the same time. This inherent uncertainty at the quantum level leads to a constant fizz and pop of virtual particles, particle-antiparticle pairs that wink into existence for fleeting moments before annihilating each other back into the vacuum. While virtual particles cannot be directly observed, their existence has been indirectly confirmed through experiments like the Casimir effect, where the pressure of virtual particles outside two closely spaced metal plates is different from the pressure between them, resulting in a measurable force pushing the plates together. The concept of virtual particles and the quantum vacuum is crucial for understanding vacuum energy. According to quantum field theory, the energy of the vacuum is not zero, but rather a small, non-zero value due to the constant churn of virtual particles and their interactions with the underlying fields. This seemingly insignificant vacuum energy, however, has profound implications for the evolution and fate of the universe. Section 6. The puzzle of vacuum energy, a cosmic mismatch. The vacuum energy predicted by quantum field theory is astronomical, to say the least. In fact, it's so large that it should have blown the universe apart in the first fraction of a second after the Big Bang. Yet here we are, billions of years later, in a universe that is not only expanding but also accelerating in its expansion. This discrepancy between theory and observation, a whopping 120 orders of magnitude, is one of the biggest mysteries in modern physics. To put this discrepancy into perspective, imagine trying to calculate the distance between the Earth and the Sun, and being off by a factor of the entire observable universe. That's the scale of the mismatch we're talking about. It's as if the universe is playing a cosmic joke on us, teasing us with a profound mystery that lies at the heart of our understanding of reality. So where does this enormous discrepancy come from? One possibility is that we simply don't fully understand quantum field theory yet. Quantum field theory is a remarkably successful theory, but it's also notoriously difficult to calculate with, especially when it comes to gravity. It's possible that there are some subtle effects that we're not accounting for that could dramatically reduce the predicted value of vacuum energy. Another possibility is that there's some new physics, some unknown mechanism that's suppressing the vacuum energy. This could involve new particles, new forces, or even modifications to our understanding of space and time itself. Physicists have proposed a number of ideas, such as supersymmetry, extra dimensions, and string theory, that could potentially solve the cosmological constant problem. But so far, none of these ideas have been experimentally verified. The mismatch between the predicted and observed values of vacuum energy is a stark reminder of how much we still don't understand about the universe. It's a challenge to our most fundamental theories and a tantalizing clue that there's still much more to discover. Solving this puzzle could revolutionize our understanding of physics and potentially lead to new technologies and innovations that we can't even imagine today.